n into n squared. Here n is called the base and the tiny 2 written at the top right is called the exponent or power. It simply tells us to multiply a number by itself. For example, 5 times 5, 25. So 5 square equal to 25. But wait, you might have a small question. Why do we write the tiny 2 at the top right? Why not on the left or at the bottom? There is actually a familiar science example that can help us understand this. Think about H2O. Here also we have a tiny 2, but this time the 2 is written below. Why? Because the position of a small number can change its meaning. In math, when we write the tiny number at the top right, it's called an exponent or power. In science, when we write a tiny number at the bottom, it's called as subscripts. In H2O, the tiny 2 tells us that one water molecule contains 2 hydrogen atoms. So even though it is the same tiny number, where we write it matters. Now you may ask, if already call it power of 2, why do we need another name square? Why? Because a square has a special property. Its length and width are equal. That makes a square very useful when we want to measure unorganized space. Imagine a traditional Chettinad house. At the center, there is usually a large open courtyard surrounded by wooden pillars. When designing a building, things like how we divide the space, how we repeat dimensions, and how we maintain proportions are all important. Let's turn this into a simple mathematical example. Imagine 4 pillars standing at the corners of a square. The distance from one pillar to the next is 8 feet. And in the other direction, it also 8 feet. So we have an 8 by 8 space. What is its area? 64 square feet, or 8 square equal to 64. Why? Because we are multiplying the same length in 2 directions. 8 times 8, 64. Same length, same width. This is the basic geometric idea behind a square. Even if you have never seen a Chettinad house, no problem. Just look at the tiled floor in a classroom or a room at home. Suppose one tile is 2 feet long. If there are 5 tiles along the length, 5 by 2, 10 feet. And if there are also 5 tiles along the width, 5 by 2, 10 feet. So, what do we call that room? A 10 by 10 room. The area is 10 times 10, which is 100 square feet, or 10 square equal to 100. So here square is not just the answer to a multiplication problem. It represents an area where the length and width are equal. That is why the power of 2 has this special name, square. Now let's take this idea into the world of computers. Suppose we want a computer to draw this 10 by 10 tiled floor. Can we simply tell the computer draw a square? Not really. A computer doesn't think about the problem the way we do. It follows instructions step by step. So we can tell it draw row 1, then row 2, then row 3, and so on. But wait, do we really have to write the same instruction again and again? No, that's where a loop comes in. We can simply say draw this row and repeat it 5 times. That is a loop. And we have one loop inside another loop. We call it a nested loop. The outer loop handles the row. The inner loop draws the 5 tiles inside each row. The outer loop runs 5 times, and each time the inner loop also runs 5 times. So 5 times 5, 25 tiles. In mathematics, 5 square equal to 25. In programming, outer loop into inner loop. In geometry, area of a square. Different words, different subjects. But the basic idea is the same. How many in one direction into how many in the other direction equal to the total. Now let's connect this to something we saw in our Pythagoras theorem video. Gnomon. How does a square actually grow? This is where we get a beautiful mathematical pattern. 1 plus 3 plus 5 plus 7 up to 2n minus 1 equal to n square. But why do these odd numbers produce perfect squares? Let's visualize it. Start with just one tile. That gives us 1 squared equal to 1 times 1 equal to 1. Now we want to make it into a 2 by 2 square. We cannot remove the old tile. Instead, we add a new row and a new column. The new row has 2 tiles. The new column also has 2 tiles. So 2 plus 2, 4. But there is one problem. The corner tile is shared by both the new row and the new column. So we counted it twice. We need to subtract 1. Therefore 2 plus 2 minus 1 equal to 3. So to grow from 1 square to 2 square, we need to add exactly 3 new tiles. That's where our first odd number comes from. Now let's go from 2 square to 3 square. We add a new row of 3 tiles and a new column of 3 tiles. Again the corner tile is counted twice. So 3 plus 3 minus 1 equal to 5. We need to add 5 new tiles and those 5 tiles form an L shape. Next 3 square to 4 square. We get 4 plus 4 minus 1 equal to 7. So we add 7 new tiles. Again an L shaped layer. And this continues 1, 3, 5, 7, 9 so on. These are the odd numbers. Each new odd number layer helps us build the next perfect square. This L-shaped layer is called a Gnomon. So in general, we have an n times n square and want to build the next square. The new row contains n tiles. The new column contains n tiles. Together n plus n equal to 2n. But the corner tile is common to both. So we subtract 1. That gives 2n minus 1. That is why the number of new tiles in each Gnomon layer is 2n minus 1. And that is exactly why we get 1 plus 3 plus 5 up to 2n minus 1 equal to n square. This is not just a formula to memorize. We can actually see why it works. We are building a square one odd number Gnomon layer at a time. Now let's move to our next idea, perfect squares. When a whole number is multiplied by itself, the result is called a perfect square. For instance, 3 by 3, 9. So 9 is a perfect square. In simple terms, a perfect square is a number that can be written as n times n. So 1, 4, 9, 16, 25 are all perfect squares. But then, what is the difference between a square and a perfect square? A square is a shape, a geometric idea. A perfect square is a number. If we count the tiles inside square shapes, we get 1, 4, 9, 16, 25. Those numbers are perfect squares. So remember, square, shape, perfect square, number. Now, let's do something more interesting. What if we use perfect squares as a special rule to create connection between numbers? Before that, we need one basic idea. What is a graph? Imagine a city with 5 important places. We can represent each place with a dot. If there is a road between 2 places, we can connect their dots with a line. In graph theory, place, vertex. Road or connection, edge. And when we put vertices and edges together, we get a graph. That is the basic idea of graph theory. Now, can we connect any two numbers we want? No. Let's create a simple rule. Imagine that each number is a dot. We connect two numbers only if their sum is a perfect square. For example, take 1 and 8. 1 plus 8, 9. And 9 is a perfect square. So we can connect 1 and 8. Now take 4 and 5. 4 plus 5, 9. Again a perfect square. So we can connect 4 and 5. But what about 1 and 4? 1 plus 4, 5. Is 5 a perfect square? No. So we do not connect 1 and 4. If we take many numbers, represent each one as a vertex and connect only the pairs that satisfy our special rule, we get a special type of graph. That is called a square sum graph. And now things get really interesting. Imagine that we can travel through this graph and visit every vertex exactly once and finally return to where we started. That closed route is called a Hamiltonian cycle. So Hamiltonian cycle is basically visit every vertex exactly once, return to the starting point. Now comes the important question. Where do we actually use this idea in real life? In our example, we used perfect squares as the rule for creating connections. But in real world problems, we don't have to use perfect squares. The important idea is the graph model. We can represent many locations as vertices and possible journeys between them as edges. For example, imagine a delivery company. A delivery vehicle has to visit many houses and delivery packages. We can represent each house vertex, possible travel between houses, edge. Now the computer can search for a route that visits all the required locations. But in real world, finding any route is not enough. We also care about distance, time, fuel, traffic, and many other constraints. That makes real world routing problems much more interesting and much more challenging. If there are only 10 or 20 locations, we might be able to think about different routes ourselves. But imagine there are hundreds or thousands of locations. Trying every possible route by hand becomes practically impossible. That's where computer algorithms help us. We first convert the real world problem into a graph model. Then the computer analyzes that graph and searches for a route that satisfies the rules and constraints we give it. And that's how our journey has grown. We started with something as simple as square, perfect square, square sum graph, Hamiltonian cycle, computer algorithm, real world root problems. So the next time you see a simple square, don't think of it as just as a shape. Because inside a square, there might be a pattern. Inside that pattern, there might be a rule. Inside that rule, there might be an algorithm. And that algorithm might one day help solve a real world problem.